Hi. Now that we have finished talking about how ionic compounds form and in what ratio the cations and anions need to be, we'll start talking about some of the properties of these ionic compounds. So when you think of an ionic compound, I want you to have in your head the picture of salt, NaCl, because that is by far the most common ionic compound that you have seen. So when you think about that and you think that, salt always comes in these like little square crystals. Why is that? Well, the reason is because if you were to zoom in on what one little grain of salt looks like, it would look very similar to this. And what we call this shape specifically is called a crystal lattice. That's what we call the 3D geometric arrangement of ions in anionic compounds. There's different types of crystal lattices that we don't need to get into in our first year chemistry class, but this is sort of the most basic and most simple crystal lattice, where you have the positive ions are symbolized here by the kind of silvery spheres, because sodium is a metal, and then the negative green looking chloride ions, and those guys are green because chlorine is a green gas. And so you can see that it sort of alternates between positive and negative ions, and since opposites attract, this is a very stable and hard compound here. So we're going to talk a little bit more about that crystal lattice. And one thing that is important is that ionic compounds form ionic solids. So at room temperature, all ionic compounds are solid, and they will have, we're going to notice that they have very high melting and boiling points. Ionic solids have these three-dimensional crystal lattice structures. And the ionic crystal lattice structure, they're held together by, what actually holds this together? Well, they're held together by very strong, we call it opposites attract, and what it really is called is the electrostatic force. And an awful lot of heat is a form of energy, so an awful lot of heat or energy is needed to break apart a lattice structure. If we're going to put salt and heat it up so much so that these particles are going to overcome their really strong attraction, you're going to need an awful lot of energy to overcome a really strong attraction, which is why they all have really high melting points. Ionic compound crystal lattices have very high melting points because it takes a lot of energy to break the crystal structure and melt the solid into a liquid. And that term, lattice energy, is a just more technical term for what you would need to add in order to do that, in order to turn the solid into a liquid and then into a gas. Lattice energy is how much energy that would take. So lattice structure strength, how strong the structure is measured in this thing that we call lattice energy. And lattice energy is a measure of the energy, and this is really kind of interesting. It's the energy released when ions are combined to make the compound, because the ions are really attracted to each other. So when they come together, that releases energy. And exactly the opposite happens when it breaks apart. So it is the measure of the forces that bind the ions together. It is also the measure of the energy needed to break an ionic solid into gaseous ions, to completely break it up, not just into a liquid, but to go actually into the gaseous phase. And the formation of a lattice structure is an exothermic reaction. This word, exothermic, we're going to use all the time, exothermic and endothermic. Anytime that you have an exothermic reaction, energy is released. So if you look at this picture over here, you can see that the gaseous ions are floating around, and then they are super attracted to each other. And when they come together, they release a lot of energy, a lot of heat. We call that lattice energy. And so when the arrow is going down, the energy comes out. Well, the exact opposite would then be true, that if you go from the crystal to the gaseous ions, like breaking them up, then that energy would need to be added in order for that process to happen. And there's many factors that can affect lattice energy. And before we go into the specifics, I want us to take a look at the next table, or the table on the next page. This looks at the lattice energy of some different ionic compounds. And so remember what lattice energy is, the energy needed to break it apart. And NaCl, that we talk about all the time, has a lattice energy of 788 kilojoules per mole. Remember that mole is 6.022 times 10 to the 23rd. So if I have 6.022 times 10 to the 23rd formula units of NaCl, I would need to put in 788 kilojoules. So when might lattice energy be lower than that? Well, lattice energy is lower than that in all these scenarios. And if you notice, there's some very big patterns, or there's some obvious patterns that are going on this table. If you notice that they're actually much higher on the right-hand side of this table. And I want you to take a look at, these type of ions. Look at the charges. Mg is a 2+ ion, and O is a 2- ion. Mg, we just said 2+, chlorine 1-. Scandium is 3+, nitride is 3-. Do you see a pattern going on? And that's actually what we're going to, or sort of the question that is at the bottom of this. And then on the left-hand side, you may notice that every single one of these, LiF, they're both +1 and -1 ions. So what is making the difference here? Why is it that LiF is 1030, LiCl is 834, and Lii is 730? Anytime that we're talking about overcoming attraction, which is what lattice energy is, we need to think about what are those factors that influence attraction. And when we're talking about the electrostatic force, it's always Coulomb's law that plays a factor in how strong this electrostatic attraction is. Think about those two pieces of Coulomb's law. One is distance and one is size of charge. If I look at the right-hand side of this table, we can see size of charge makes a big difference. When I have a 3+ and 3- ion, it takes an incredible amount of energy to break that apart, as opposed to just a 1+ and 1- ion. But then, charge does not explain why I see a trend in the positive and -1 ions, right? LiF is +1 -1, LiCl +1 -1, Lii +1 -1. So if it's not charge, it must be distance. Remember, that was the other piece of Coulomb's law. And if we go back to this graphic organizer right here, we'll see that that's exactly what this says. The lattice structure strength depends upon the number of charges on the ions and the size of the ions, right? It's two different measurements that can influence the size of lattice energy. Lattice energy increases as the size of ions decreases. And this is all back to Coulomb's law. Smaller ions with crystals are held closer together, and that means that the electrostatic attractions are greater. Larger ions with lattices are held further from each other, and less lattice energy is needed to separate them. That's that other part of Coulomb's law. The further two particles are from each other, the less attraction there is for each other. And then we go to lattice ions with a higher charge. These have much greater lattice energies. We saw that on the table on the next page. And it gives us the example that magnesium oxide has 2 plus and 2 minus ions, and it is much larger than Na plus and Cl minus. Right? And so these were the trends that you should have seen, or that you will see. That greater charge, the greater the charge difference equals larger lattice energy. It's going to take more energy to break it up. And smaller ions equals larger lattice energy. Think of where the smaller ions are. They're at the top of the periodic table. So that's why when you look at, let's say, the NaF, fluoride is at the top, then it's Cl, then it's NaBr, then it's NaI. Iodine is the largest of the halogens, therefore the ions are the furthest apart, and it only takes 682 kilojoules to break up. Where NaF, fluorine, is the smallest of the halogens. The ions are closer together, Coulomb's law. It's going to take more energy to break it up.